this video I want to look at the contact in more detail. Previously we had stresses that were in tension, which doesn't make sense within the contact. Contact should be in compression unless there's some form of adhesive there, which is not the case here. So to get more control over the contact and where it's actually making contact, I'm going to split some surfaces. So offset from plane, and the pins are 10 millimeters in, so let's have one at 9.5, going the other way. One plane there, and one the other side. So there are two planes. We're going to use those planes to split this surface so that there's now a narrow band on the red surface where the contact is going to be allowed to occur. And we're going to do something similar with the pins, or the bottom pin at the moment. I'll leave the top pin alone for now. So let's make these invisible, we don't need them anymore. Create a new plane, offset from plane here. Now the pin's at 10 millimeters, but we're going to go slightly further, minus 10.3, and another one at minus 10.7. And again we split. Use this plane to split here, and a second plane to split here. Again, we can make these invisible now. But you can now see there's this narrow band here that we can say that's where the contact occurs when we go into ANSYS. So let's do that. Save. Once again into engineering data. Data sources, general materials, add aluminium, composite materials, we want the honeycomb, so let's start by having a coordinate system, because we need to add one of those. Insert coordinate system, global coordinates at 0, x leave alone, change y to z, and define geometry selection on this. Z is vertically upwards. And let's change the name to coordinate system for core. Then we can apply our materials. The pins are steel, the core becomes honeycomb using the coordinate system for core. The skins become aluminium. Connections, this is where we have to be careful. Rename. All bonded. The core to the skins need to be bonded. The pins become no separation. And we need to be careful about what surfaces are actually in contact. Let's change, actually, that's because we should keep track. That's the bottom pin. rename again. Okay, so no separation, pin bottom to skin bottom. Now you can see there are two faces in contact, but really we only want the one, so let's control click to get rid of this. And you can see now that there's only that narrow band in contact there, and it's in contact with that band in blue on the opposite face. So constraints 1, 2, 3, 4, insert frictionless 1, 2, 3, 4, 5, insert frictionless. We need to fix a pin at the bottom, insert fixed. And here we have a displacement, insert displacement, leave the X and Z free, but the Y comes down -1 millimeter. The last thing we need to do is the mesh. So one bodies, 1, 2, insert sizing 0.5, core, insert sizing 0.5, skins, insert sizing 0.25. Let's have a look at that. Rename. Now the other thing we can do is specify finer geometries of meshing in the contact. So let's choose faces this time. We want that face, that face, insert sizing 0.15, mesh, generate, see how many nodes we've got. So just over 200,000 nodes. Now the other thing we can try to do, see what effect it has. Let's choose that edge and insert a refinement. Because the idea is to have a better mesh in this contact region, but we'll see how this works out. Unfortunately, the number of nodes has gone well up because it's changed everything everywhere. Let's delete that. But what we can try instead, insert sizing. It has improved the mesh density on this face. Perhaps not in an ideal way, but we're still within the node limit, so let's solve this and see what happens. Okay. Now what I'm particularly interested in is the normal stresses in the y direction. Stress, normal, y. Now they still have these little red spots here, but let's just look at the pins by themselves. That blue region is what we expect to see. The red region suggests that there is still part of the contact that doesn't actually want to be in contact. We'd need to go back and just shift the planes, the work planes slightly to improve that. But we haven't improved the stresses here. We still have this compressive, tensile contact in the edges of this. So I think the meshing here would need to be a lot better to really address that problem, but it's a very strange behavior. So there has been some improvement to the contact. So I am going to make a slight change to the inventor file. Now that was minus 10.3. If we make that minus 10.4 instead. And we'll move the other one as well. Minus 10.8. So we've shifted them to the right, towards the middle. Save. Geometry. Update geometry from source. And this is the thing to watch out for whenever you do an update geometry. It's added in another contact region. Let's just suppress this. Don't want this one. But what about skin? Bottom to pin bottom. It's still there. That's the one we do want. Let's just check the other side of that. It's still one face to one face. You can see the blue region where it's making contact. So let's solve again. Well, that went spectacularly wrong. I think the blue region is not coming in contact with the red region. So we need to move that as well. There's an unexpected lesson learned. So, minus add 0.3 to that. Suppress that again. Fingers crossed. Solve. Much better. And you can see even that little red spot has vanished. Let's have a closer look. What does that mean? Okay, now it's almost entirely compressive, as you would expect. There is some small amount of tension here, but it's only very small. Obviously, if you continued adjusting that contact region, it would improve. But that's not bad at all. Let's look at everything. Show all bodies. And just for curiosity, let's look at von Mises. Because we fixed it here, the stresses have changed. I actually need to fix this as well before I say that. Very slightly. Obviously this needs fixing as well. But if we're particularly interested in the composite layer, the core rather than the skins, because he's just aluminium skins, and we understand the behavior of those. If we want to look at the core, then what we can do is let's just look at the core. And I'm going to say this surface, I want to see strain, shear strain in the XY plane. Good. Solve. Now there is some, it's not entirely uniform because of the slight asymmetry in the loading. You can see there's a gradient of strain going from one edge to the other. If you want to look at this more carefully, I mean you can use probes of course, but if you want to look at this in a different program, you can right click and export. But it's worth, before doing that, go to Tools, Options, Export, make sure it says Include Node Location before you do the export. So, right click, Export Text File, calling it Strain XY Core. You can choose to save it as Excel or text, but I don't think it changes the format. Save. And you can open it up in Excel either way. And what you have is one or two lines at the top that tell you what the file is about. This is the number of the node. Then you have X, Y, Z locations of the node, and then you have the value that you're exporting. Sometimes these files have additional information. They can have, having got to the end of what you've exported, it can then tell you about how the different elements are constructed within the file. In this case it's quite simple. You just have the strain data. So you can open it in Excel or you can open it in Matlab. I'm sorry, I should have started this earlier. Here's what I did earlier, obviously. The command to read the data in is dlm read. So you say data equals dlm read, the name of the file in apostrophes. Then the next argument is \t, which tells the Matlab there are tabs between the different columns. And the 1,1 says that's the first row, or the second row because it starts from 0. So 1 says skip the first row, the first line. And the one here says skip the first column, in other words the node numbers. So what we were interested in are the X, the Y, the Z and the strain. So we can see, having read the data, we can say X equals data, all the rows in the first column, and we can then say strain equals data, all the rows in the fourth column, plot them against each other, X, comma, strain, and let's turn them into black dots. So that's a way of plotting strain against the longitudinal position. And this at 0 I believe is the middle of the beam because that's where we specified the general coordinates. So 0 is the middle of the beam, and then you can see it tailing off again at once you go beyond 20, which is where the loading pin is, the supporting pin. Once you go that, it tails off towards 0 at 30, which is the edge of the beam. So that gives you a way of plotting strain with position in the beam. I haven't tried this yet, but what happens if you plot it against Y? It's probably a mess. Helps if we define it first. Y is the second column. And let's define Z as well. Okay, that is useless. And Z. The width of the beam is 12, but we've quartered it so it becomes 6. So you can see a slight change of maximum strain as you're going up through the width of the beam. But that's not not terribly useful thing to plot. No, definitely the X is more interesting. Because apart from anything else, it gives you quite clearly where the maximum strain is, both in terms of what the value of the strain is and where it occurs in the beam. Now I've just exported the data for the surface. You could choose, I think, to export the data for the entire solid of the core, and perhaps you would get something similar to this. So that's all I wish to say in this video. Thank you for listening.